Welcome to the 8th lecture in abstract algebra. The topics that we'll explore in this lecture include the trigonometric and exponential forms of complex numbers, algebra on circles, and an introduction to binary algebraic structures. Okay, so I'll start by reminding you of two trig functions. So recall that sine and cosine are periodic functions with period 2 pi. That is, cosine of theta is the same as cosine of theta plus 2 times pi times n, and sine of theta is the same as sine of theta plus 2 times pi times n, and this is true for any choice of integer n. Okay, so now we're ready for a new definition. An argument of the complex number z, which we'll denote as an ordered pair of real numbers x and y, is a real number theta such that the real number x is equal to the modulus of the complex number z times the cosine of theta, and the real number y is equal to the modulus of z times the sine of theta. So notice that if theta is an argument of the complex number z, then theta plus 2 times pi times n for every choice of integer n is also an argument of the complex number z. The set of all arguments of the complex number z is denoted arg z. Notice the lowercase a. Okay, so now we're ready to define the trigonometric form of a complex number. The trigonometric form of the complex number z equals the ordered pair xy is z equals the modulus of z times the ordered pair, whose first component is cosine of theta and the second component is the sine of theta, where theta is an argument of the complex number z. All right? So next I need to remind you of some trig identities. So recall the following trigonometric identities. the cosine of a sum or difference is equal to the product cosine alpha times cosine beta minus or plus, notice that the sign changes depending on whether we are using a sum or difference, times the sine, or with the product the sine of alpha times the sine of beta, and the sine of a sum or difference is equal to sine alpha cosine beta, plus or minus, the sign remains the same, the product sine beta cosine alpha. Alright, so next we'll use these trig identities to prove a lemma. So let z sub 1 be the modulus of z sub 1 times the ordered pair cosine theta 1 sine theta 1, and z sub 2 be the modulus of z sub 2 times the ordered pair cosine theta 2 sine theta 2. These are two complex numbers in trig form. Then the product, z1 times z2, is equal to the product of the moduli times the ordered pair, where the argument of the trig functions is the sum of the arguments of the two respective complex numbers. Okay, so proof. Z sub 1 times z sub 2 is the modulus of z sub 1 times the ordered pair cosine theta 1 sine theta 1 times the modulus of z sub 2 times the ordered pair cosine theta 2 sine theta 2 theta 2 so we can regroup these and start with the product of the moduli, and we'll actually perform the product of the two ordered pairs. So we have cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2 as the real component. And we have cosine theta 1 times sine theta 2 plus cosine theta 2 times sine theta 1 as the imaginary component. So using our trig identities, we can restate this as the product of the moduli times the ordered pair, whose real component is cosine of the sum theta 1 plus theta 2, and whose imaginary component is the sine of the sum theta 1 plus theta 2. Okay, so as a corollary, we will focus on the relationship between the arguments of the two complex numbers and the argument of their product. I will state it this way. The set of the arguments of the product, z1, z2, is equal to the set of arguments of z1 plus the set of arguments of z2. Now, this is what we call an identity equation. So this identity holds where this identity means that if any two values of arguments are specified, then there is a value for the third argument such that the equation holds. So the proof is quite simple. If theta 1 and theta 2 are specified arguments of the complex numbers z1 and z2 respectively, then by the previous lemma, the sum theta 1 plus theta 2 is an argument of the product z1 times z2, and clearly the identity theta 1 plus theta 2 is equal to theta 1 plus theta 2, or rather the equation theta 1 plus theta 2 is equal to theta 1 plus theta 2 is an identity. All right. So recall that the cosine function is even while the sine function is odd. That is, cosine of negative theta is the same as cosine of theta, and sine of negative theta is the negative of sine theta. All right. Okay, so next we move to powers of complex numbers. We'll start with the definition. For every complex number, we define the 0th power of that complex number to be the real number 1. All right, so next we'll prove a very useful theorem known as the Moivre's theorem. If C is given in trigonometric form, and n is any integer, then z to the power of n is the quantity, the product of the modulus of z with the ordered pair cosine theta, sine theta, raised to the power of n, which is the modulus of z to the power of n times the ordered pair cosine n times theta sine of n times theta. All right, so proof. The case n equals 0 is the statement z to the power of 0 is the modulus of z to the power of 0 times the ordered pair cosine 0 times theta, which gives us 0, and sine of 0 times theta, which gives us 0. Any real number to the 0th power is the number 1. Cosine of theta is 1, sine of theta is 0, and so this is the real number 1, which is true. So next, we prove that the statement z to the power of n is equal to the modulus of z to the power of n times the ordered pair cosine times n theta sine of cosine of n theta and sine of n theta. We'll prove that this is true for all positive integers n. So our proof will be by induction. The case n equals 1 is the statement z to the power of 1 is the modulus of z to the power of 1 times the ordered pair cosine of 1 times theta sine of 1 times theta, which is simply the trigonometric form of the complex number z. And so this is true. So we assume the case k minus 1, that is, we assume that the statement z to the power of k minus 1 is equal to the modulus of z to the power of k minus 1 times the ordered pair cosine of k minus 1 times theta sine of k minus 1 times theta. We assume that this is true. Then z to the power of k is z times z to the power of k minus 1, which is the modulus of z times the ordered pair cosine theta sine theta times the modulus of z to the power of k minus 1 times the ordered pair cosine of k minus 1 times theta sine k minus 1 times theta. So this gives us the modulus of z to the power of k minus 1 plus 1, or simply k, times the ordered pair cosine of theta plus k minus 1 times theta, which gives us k times theta, and similarly sine of k times theta. Hence, the case k minus 1 implies the case k. So by induction, we have that z to the power of k, well, let's restate it, z to the power of n is equal to the modulus of z to the power of n times the ordered pair cosine of n theta, sine of n theta. This statement is true for all positive integers n.